I want to bring on Dr. Kevin Perry. I've been so fascinated by his story and have not had the chance to hear him speak. So I'm absolutely thrilled to have him here tonight. He's an associate professor in the Department of Atmospheric Sciences at the University of Utah. He served as chair of the department for some time from 2011 to 2018. He holds a degree in meteorology, his bachelor's from Iowa State University, and a PhD in atmospheric sciences from University of Washington. He's participated in more than 20 air quality projects, ranging from local scale pollution events to the intercontinental transport of pollutants. For the last 5 years, Dr. Perry has focused his attention on dust plumes originating from the exposed portions of Great Salt Lake and the lakebed. So I'm thrilled to have you. I think your work is really important. And as the lake shrinks and shrinks and shrinks, as we're seeing, this shoreline becomes more exposed and your work becomes critical. So I'm just really thrilled to turn it over to you.
Well, thank you for that introduction. And I just want to give just a little tiny brief history of how I got interested in dust. And that was when I was at a postdoc at UC Davis. I was working for the National Park Service doing air quality studies for the National Park Service, and would spend the summer doing maintenance on the equipment in the winter time trying to analyze the data. And we started noticing that there was a lot of dust in the eastern half of the United States during the summertime. And its chemical composition was unlike anything from North America. And we eventually traced it back to its origin in Africa, that there was basically a lot of dust being transported across the Atlantic in the trade winds and into the eastern half of the United States. Later on, I started studying the transport of dust from Asia to North America and the pollutants that came with it. And so it's not a big leap to see that I was interested in trying to understand a local dust source as well. And so what I get to talk about today is a really crazy scientist doing a really crazy thing about something that I really care about, and I think that's something that's really important. And so I spent 2 years of my life basically trying to understand all different quadrants of the Great Salt Lake, playa. So if you were here back in the 1980s, which I was not, the lake looked something like this, very different than it does today. It was the 4th largest terminal lake in the world. And the lake elevation was just peaked out at a little over 4,211 feet. Fast forward to 2016, and you can see a remarkable difference in the elevation of the lake. And there's more than 750 square miles of lakebed is now exposed. And to put that into perspective, 750 square miles is about the exact same size as the Hawaiian island of Kauai. So it's actually quite expansive. And so this picture was taken in December 2016. Just the lake was about at its lowest, but here's what it looked like yesterday. So this is a satellite image. You can see the north arm and the south arm being different colors from what was explained before. And you can see most of Farmington Bay is basically exposed with the Jordan River inflow into the lake as well. And Gunnison Island up in the northern part of the lake is looks like it's attached physically to the land mass again, making it not an island, which is not great for the pelicans. We also know that the long-term trend in the Great Salt Lake elevation is downward. There's a lot of variability due to weather patterns, but superimposed on that long-term variability is the result of water diversion, as was talked about earlier. And the long-term trend is about ½ a foot per decade. And I have obviously long-term concerns about the future of this lake. We've seen what happens to other terminal basin lakes when we divert too much water. The Aral Sea disappeared, and there's countless examples of that around the world, and I would hate for that to happen here. So, why do these water diversions matter? Well, they obviously have impacts on the bird habitat, and they alter the salinity specifically in the southern arm, and that could threaten the brine shrimp industry. It makes extracting minerals from the lake more expensive because they have to dredge more and pump more longer distances to get to the minerals. And it makes it more difficult for the recreation and the boating opportunities. But what I'm here to talk to you about is the increase in frequency and severity of dust storms. These dust storms can impact our visibility. Dr. Mackenzie Skiles at the University of Utah is doing a lot of work on the impact of that dust on the snowpack and how it affects the water availability. And there's also a potential for this dust to have human health impacts as well. So here we have a webcam footage from the University of Utah looking at downtown. So we're looking to the west. The Great Salt Lake is to the right. And we have a cold front that's passing through, and it's picking up dust off of the Great Salt Lake and bringing it into the city. And you can see it has a dramatic impact on the visibility, and it's a potential health impacts associated with that as well. And so I was basically funded by DNR and the Utah Division of the Facilities Construction and Management to try and identify, what parts of the Great Salt Lake were acting as dust sources, and how might fluctuations in the lake level impact future dust production. And they also wanted me to determine if there were any heavy metals in the dust that might pose a threat to human health. So I started off on this large odyssey to try and do that. But in order to do that, I had to kind of understand the issues that are important for dust production. One of those things that controls the dust emissions from the soil is the fraction of silt and clay. So that's the smallest particles, the ones that can get lofted into the air. And then, there's a surface crust over much of the Great Salt Lake. I didn't know how much or to what extent it was there. But if you have a strong crust, it's going to prevent the erosion of the dust. And then vegetation plays a role in that as well. And we really didn't know how much fine soil was out there. We didn't know the surface crust characteristics. And we had a little bit of idea of how much vegetation was out there, but not the full extent of it. And so those are kind of physical sorts of things with the playa that's out there. But you also need to have dry soil, and you need to have strong winds in order to generate the dust. So there's a whole bunch of things that are necessary to generate dust. And so I wanted to do a full survey of the entire Great Salt Lake. And so I divided it up into what we call decision units, large areas that should have similar geology, similar sources, that sort of thing. And each one of these decision units were then divided up into subunits. And the idea was to do 4 kilometer by 4 kilometer boxes and then do some detailed sampling in each one of those subunits. And here we're looking at the southern part of Antelope Island, and we're looking at decision unit 2 and several different subunits. The subunits are defined by these polygons. And in each one of those polygons, I basically set up a GPS grid that was nominally about 500 meters apart. And at each one of those locations, I would go out to those predetermined coordinates and catalog the surface crust characteristics, the vegetation amounts, and also collect a soil sample. And I would collect all of those soil samples from a single subunit and put them into one bag, basically to try and get a representative sample. And how did I get to all of these places? By bicycle. This is where the crazy scientist comes in. So I decided to do this on a bicycle and trailer system. I call it the University of Utah Dust Devil. So why did I want to do it that way? Well, for one, it's low cost, it's low impact. If you look on the right, we have some ATV tracks that are out there. And then in the middle of the ATV tracks, you can see the tracks from the bicycle are much less intrusive on the lake bed itself. Theoretically, the bicycle won't get stuck although that is not completely true. It is possible to get stuck out there. The worst I ever got stuck, it took me about half an hour to get the bicycle and trailer system out. Of course, the disadvantages of this are that it's slow, it's really physically challenging, and you have to have the weather cooperate. You have to wait for at least 5 days after the rain. So, some people have always asked me, why don't you just use ATVs? Well, here's a good reason not to use ATVs. I was actually forced to use one on the Utah Test and Training Range. They insisted that I not ride a bicycle out there, then they were going to come out with me. I told them it was a bad idea, but this is what we ended up doing. We had wonderful sampling for the first hour and a half. We got stuck and we spent the next 9 hours digging it out and basically trying to figure out how to get off of the lake bed with the equipment. So that damage, unfortunately, was severe, and it's probably going to be there for a really long time. So what did I do? Well, I spent more than 100 days, more like probably 140, 150 days out on the Great Salt Lake bicycling. Bicycled a total of 2,300 miles to do this. About 90% of it was able to be ridden. About 10% of it was too soft to ride on the bicycle, so I ended up pushing the bicycle about 10% of that. Doesn't sound like much until you think that's 230 miles of pushing a bicycle. I collected more than 5,000 samples and surface crust observations and collected almost 3 tons of soil to bring back to the lab. And I'm just going to jump right into the results real quick. So remember that one of the criteria for dust production is having a lot of silt and clay. So those are the small particles. And it's not surprising that the highest concentrations of silt and clay are kind of located near where you have inflow from the Weber, the Bear, and the Jordan River. So in Farmington Bay, specifically the eastern side of Farmington Bay, we have higher amounts of fine soil. We also have higher amounts of fine soil down at the southern part of Antelope Island. There are some drainages that come in there, Goggins Drain and some others that can leave fine soils as well. The western side of the lake has much smaller amounts of this silt and clay, so has less parent material that can act as dust sources. If we look at the northern half of the Great Salt Lake, you'll see Bear River Bay. Entire area of Bear River Bay has a lot of silt and clay from the Bear River. And so that is an area that has a lot of parent material, but much of the northern arm has very small amounts of this fine material, with the exception of the extreme northwestern quadrant of the Gunnison Bay. So the surface crust conditions. So I needed to know, what the vegetation percentage coverage was, and I needed to know the surface crust thicknesses. So I kind of divided it into thick crust, which was bigger than deeper than a centimeter, moderate crust, and shallow crust, which was less than half a centimeter thick, in areas with no crust, and then looked at lots of different features. I was blown away by the variability of the surface crust out on the Great Salt Lake. And then you see really strange things out there. Here's an example of one of these rocks that have moved on their own due to forces as yet unexplained. And there's lots of fascinating geologic features and artifacts that are out on the Great Salt Lake as well. So I got some pictures just to kind of show some of the variability. So here's an example of thick crust. It's eroding. And you could go out here and you could pick up one of these pieces of thick crust, and it's almost like a dinner plate. It's that hard. There is no intact thick crust anywhere on the Great Salt Lake. Anytime you find thick crust, it's eroding away, which implies that it was formed at some point in the past and is now eroding over time. So there's one example of thick crust. Here's another example of thick crust. And this is pretty robust. You could probably drive ATVs on this without any issues at all. But there's not a whole lot of thick crust out there. And then we have moderate crust. Here's what I refer to as an erodible moderate crust. It's easily disturbed, but it's between about 0.5 centimeter and 1 centimeter thick. Here's another example of that erodible moderate crust. This one happens to be kind of curling up on the edges. You can see that if you drive anything across there, you'll break off those edges and it'll end up being a dust source. And then we have shallow crust. In my naive ideas, preconceived ideas, I thought this was going to be what I see the most of out there, and just uniform shallow crust. And that's there are areas where it's like that, but that's not the norm. So here we have shallow crust with little tiny pebbles on top of it, and there's a dust storm in the back. You can see some white dust being blown way off in the distance. The shallow crust really is pretty shallow. Here, less than 0.5 centimeter, and it's pretty fragile. Sometimes you find areas where the crust is basically curling up on itself and easily dislodged by activity or wind. And then there are some areas where there's no crust at all. I didn't like these very much. It's impossible to ride your bicycle across the sand, and so you end up pushing. But there are areas out there on the Great Salt Lake where you have sand dunes on the exposed portions. And then you have areas out on the lake where there's been a lot of ATV activity that has completely destroyed whatever crust was there. I have no idea what kind of crust was here before the ATV activity, but there's clearly no crust available, and this is one large source of dust. So, and kind of looking at overall of these 5,000 data points across the lake, 67% had shallow crust, 4% basically had a moderate crust, and 1.5% had a thick crust. So you add those all together, and you're basically almost 3/4 of the lake is protected by a crust of either shallow, moderate, or thick crust. And about, just like 26% of the lake has some form of eroding crust or no crust at all. So I kind of look at that as, 25% of the lake is a potential source, and 75% is currently protected. And so how do we identify these dust hotspots? Well, the dust hotspots are places where you have a shallow crust or no crust, little or no vegetation, and you have to have enough fine material to actually be a dust source. And so what do these dust hotspots look like? Well, here's an example where you have a thin crust, a shallow crust that's been eroded and by the wind, and the material underneath of it in the middle is actually been deflating and blowing away. Sometimes these dust hotspots merge. Well, we'll get to that in a second. Well, here's an example of how thin that crust actually is. That protective crust at this location was really thin and was eroding away. And sometimes those areas merge together into a large dust hotspot. These aren't real common out there, but there are some areas where that is the case. So where are these dust hotspots located? So all of these red dots are places where all of those criteria were met. So we have a significant dust hotspot over in Farmington Bay. That's the one that has the biggest potential impact on the people that are living in Salt Lake City and along the Wasatch Front. We also have some dust sources over on the western side, fairly close to the US Magnesium production facility over there. And luckily for Tooele anyway, the southwestern portion of the Great Salt Lake doesn't have a lot of dust sources right now. Now, if we look at the northern part of the lake, the northwestern part of the lake is really the only part up there in Gunnison Bay that has any significant dust sources. But Bear River Bay is an area where we had a lot of those fine materials, and we have crust that is eroding away that gives a lot of potential dust sources. So really, we have the hot spots all over the different parts of the lake, but my estimation is that only 9% of the lake is currently generating dust plumes, and that a maximum of 22% of the lake has enough fine material to be a dust source if we were to disturb that protective crust. And the next question was, how do this fluctuating lake level might impact future dust production? Well, the state of Utah actually funded a study in 2016 to use an aircraft to fly over and have a laser beam pointed down to measure the elevation of the lake bed very accurately and creating a digital elevation model. And since we have that model and I have all of these locations of what these dust hotspots are, then I can put those together and I now know the elevation of every single one of those dust hotspots. And we can look at Farmington Bay and we can look, the x-axis is basically the Great Salt Lake elevation. And the y-axis is kind of a frequency distribution. It basically tells you what fraction of the dust hotspots would be covered by water at a given elevation. And you can basically see that it's linear, which I hadn't really expected, and it has a slope of about 14% per foot. But you'll notice that my dust hotspots were all, at least 2 or 3 feet above the current elevation of the lake, which is 4192 and a half right now. But basically this gives us an idea of what the lake level would have to be to cover up the dust hotspots. And we did this for Farmington Bay. We did it for each quadrant of the lake, and they tell a similar story, slightly differently. This is the Bear River Bay area. It's a linear relationship, about 13% per foot, but you'll notice that the dust hotspots are a much higher elevation. And you'd have to have a significant increase in the lake to cover up any of the dust hotspots that I observed up there. And then we have Gilbert Bay, which is the southwestern quadrant, very similar to Farmington Bay. And then we have the northwestern quadrant, and the slope is very shallow up there. It's about 7% per foot. And you'll notice that also you have to be at least 3 or 4 feet higher than the current lake elevation to cover up any of the dust hotspots that I found up there. So, the summary of that one is that these dust hotspots are very linearly with lake elevation, and the number of dust hotspots is really not going to increase in any of the locations except for Gilbert Bay, because the Bear River Bay is already pretty much completely exposed. Farmington Bay is almost pretty much completely exposed. And the Gunnison Bay, any further reductions, you'll have a very thick salt crust that'll protect. So, Gilbert Bay is where we might have increases in dust production if the lake continues to drop. But the nice thing about it is Farmington Bay is actually the easiest area to mitigate. You can cover up 50% of the hot spots with a lake elevation of about 4198, and you can get 80% mitigation by 4,200 feet. It's not quite as easy on the other ones. But now at least we have the data to understand the relationship between lake elevation and the dust production capabilities of the lake. And the last thing I'm going to hit real quick is trying to determine if there are any heavy metals out there that we need to be worried about. And just looking at the composition of the dust out there, it's really enriched in what we refer to as evaporite minerals, which is not surprising. And the most common elements out there are calcium and magnesium and sulfur, strontium, chlorine, lithium, and boron. Normal soils are different. They're usually dominated by silicon, aluminum, iron, calcium, etc. But we were able to measure 54 different elements. So at all of those different 122 different subunits out there on the lake. And we really basically were comparing these to the EPA standards for soil. The EPA has set these regional screening levels to determine if the concentrations of species in soil pose a potential risk to human health. And the reason I say potential is because just because you have high concentrations in the soil doesn't mean that it's dangerous to humans if they're not exposed to it regularly. So there's a two-part thing here. You have to have high concentrations in the soil, and you have to have common exposure. And we don't honestly know how frequently people are exposed to the soil. But we do have data now on whether or not there are things in the soil that we need to be concerned about. And so these regional screening levels are established for residential exposure and industrial exposure. If the concentrations are less than the regional screening levels, then they're considered safe. And if the concentrations are greater than these regional screening levels, then we need to figure out how often are people exposed to it. And I just want to hit one element, and that's basically arsenic. Arsenic, every single measurement that I took of arsenic was higher than the residential and industrial screening levels, basically indicating that if people were exposed to this dust frequently, then it might pose a potential health hazard. And the question that people always ask is, well, is this natural or is this coming from industry? And one of the things that we can do to try and get information about that is to look at the variability of the species around the lake bed. If it's rather uniform around the lake, then it's going to be natural. If there are hot spots, then it's more likely caused by an individual source or sources. And if we look at the coefficient of variation, which is basically looking at how much variability there is, arsenic is very uniformly distributed around the lake, which tells me it's mostly natural. There are elements that are very, that have a lot of variability, copper, sulfur, silver, phosphorus, chlorine, etc. And I just want to show an example of copper. So copper had a couple of measurements that were greater than the regional screening levels, but most of them were well below. And the ones that exceeded the regional screening levels are located right where you would expect, basically right next to the tailings pile for the copper mine. And you basically have dust that is blowing occasionally from the copper tailings pile out onto the Great Salt Lake. Lake bed, and you can see that in the soil there. And so I just want to summarize there to say that arsenic is that only element that every single measurement was something that exceeded the regional screening levels. There were 8 other elements that had some values that exceeded either the residential and industrial or the industrial or regional screening levels. And we would refer to those as contaminants of potential concern. But the next step in this process is really to try and better understand how frequently people are exposed, because that's really going to drive whether or not this poses a health hazard. And I really want to have a special thanks to all of the private landowners and public landowners and managers that provided me with permission to cross their land to get to all of the different crazy places along the Great Salt Lake. A lot of them are very difficult to access if you can't cross private land. And I just love that little picture out there a little too late in the day. I should have been off, but you got beautiful pictures and I really enjoyed my time out there and what I was able to learn about the ecosystem. So I'll stop there.